Let's look at an application of the divergence theorem. The complexity of a surface integral is often a function of the piecewise continuity. So when we have surfaces like cubes where you've got all of those edges, that makes for more computations. So for instance, say we're given a positive constant A and we construct 6 different planes to form a cube, a solid which is bounded by the surface of the cube. So we have x equals 0, x equal a, y equals 0, y equal a, z equals 0, and z equal a. So we can think of this solid region Q here, which is defined by x running from 0 to a, y running from 0 to a, and z running from 0 to a, as bounded by the surface, just like we think of a region in the plane being bounded by a curve. So again, the region Q is bounded by this particular surface. So what we want to do is to compute the flux across this particular surface. And this is where the divergence theorem comes in very handy. Here's our vector field, x squared, z squared, comma, negative 4y, comma, 5xyz. And in order to use the divergence theorem, we must compute the divergence, which is just the sum of the partial derivatives. So we get divergence of f is 2xz squared minus 4 plus 5xy. And so now the divergence theorem says that if we want to compute the flux f across the surface, it can be replaced with the triple integral of the divergence of f over q. So this is a remarkable result, and physicists and engineers applaud this theorem because it makes their work much easier. So now we can move to the triple integral, which even though it takes some time to do, the calculations are easy. So again, all of the integrals will run from 0 to a, as you see here, the x, the y, and the z, and we simply replace the integrand with the divergence. So first we will just integrate with respect to x, very simple integrals. We get an x squared, z squared, the 2 absorbs. We get a negative 4x and a 5/2 x squared y. And now nicely here, the 0 in the bottom will actually annihilate everything. That is, we have an x in everything and the 0 gives us 0. So we only have to worry about the a. So that's going to give us an a squared z squared, a negative 4a, and then of course a 5/2 a squared y. Now we integrate with respect to y, very simple. That will give us a squared z squared y minus 4ay plus, now we have add 1 divided by the new power, 5/4 a squared y squared. Again, the lower limit zeroing out the antiderivative, so we just apply the a, and that will give us an a cubed z squared, and then of course a minus 4a squared, and then here of course we'll get a 5/4 a to the 4th. Now integrate with respect to z like we're doing very simple calculus 1 integrals. We have add 1 divided by the new power, so we get a cubed z cubed over 3 minus 4a squared z plus 5/4 a to the 4th z evaluated from 0 to a. And of course the a being the only limit that gives us something other than 0. So upon substitution, we get a to the 6th divided by 3 minus 4a cubed plus 5/4 a to the 5th. So what we're seeing here is basically analogous to what we saw with Green's theorem. The line integral, which could be difficult, can be replaced with a simpler double integral. So again, we see the value of the vector calculus theorems in work in science, mathematics, engineering, etc. And we are done.